Welcome back. I'm Kevin Tokoph. Make sure to like this video and subscribe to the channel for future videos and notifications. In this video, we're going to finish up what we did in the last videos where we started talking about polarizability. But in the last video, we looked at the mathematics behind it and the physics as well. Now we're actually going to look at the abstract theory. And for this, I'm going to consider three anions here. I'm going to consider fluoride, chloride, bromide, and iodide. All right, so here's what we have to worry about. Remember, fluoride is highest on the periodic table, iodide's on the bottom, so it's the biggest atom, or ion in this case. Well, if we're looking at an atom itself, it's a sphere. So if we're looking at the volume of that halogen, it's 4/3 pi r cubed. Okay, that's the volume of any sphere, where r is the radius of the particular atom. Now, the volume of the halogen is not equal to the volume that an electron can occupy. Remember, electrons are contained in orbitals, right? And so orbitals don't actually occupy the whole volume of the atom. But we can say that the volume of the halogen is at least proportional to the available positions that the electron can occupy, or in other words, the volume of the halogen is proportional to the volume that the electrons can occupy. That's another way of saying this. In other words, as the atoms get larger and larger towards iodide, there's more volume for the electrons to occupy. And that's going to come in handy knowing that potential energy drops as the radius of an atom increases. Okay? And we'll talk about that more in a little bit. But suffice to say, iodide is the biggest, has the biggest radius, has the biggest volume overall, and has the most volume for any electron to occupy. Okay, so hopefully that makes sense. Now what I've done is each one of these I've indicated 10 electrons. Now, they may not have 10 electrons, like iodide's going to obviously have a lot more, but it's to illustrate the point, and even though iodide, bromide have more electrons than fluoride, this actually still works, okay? It still works. So we're considering these anions, okay? Here's what I've done. I've basically taken a fraction of the atom's space, and I'm saying I'm going to put all the electrons in that region, okay? So if this is a circle, this is 1/4. So technically, if I'm doing this in a sphere, it'd be, I think, 1/8 of the sphere. Okay, 1 octant of the sphere. Okay, so I'm basically putting all the electrons in 1 octant of the sphere. Okay. Notice, and hopefully you can see this just by visual inspection, that in fluoride, if I put all the electrons in that little octant right there, they're very close to one another. Whereas in iodide, notice that because it has a much larger volume, even though I put all the electrons in that area, that 1 octant, they're still much farther apart. Remember what we talked about. Whenever you have two charges separated by a distance, a voltage develops. And when you have a voltage, you have a potential energy. And remember, systems like to get to a point where the potential energy is minimized. Okay? They don't like to have a lot of potential energy. They want to release it in some way. That's going to become important to remember that. That's true in normal physics. It's true in the organic level as well. All right, so notice what I did here. I have chloride right here and iodide right here. I have the electrons situated in each, such that what you're supposed to get out of the picture on this left one and this left one is that the distances between all the electrons are maximized. Remember what we said? When you maximize the radius, so the radius goes up, the potential energy goes down. So in theory, in the left one of chloride, this should have lower potential energy than this one on the right, because in this I have all of the electrons that I've indicated in 1 octant. They're closer together, so in this case, because the radius has dropped between the atoms, then I should have higher potential energy. Okay? Now, there's one other thing that happens here, okay, that's really important. And you have to sort of think of potential energy in this case like a vector, okay? There's a potential energy between each of these electrons in the nucleus, which is essentially a point charge for our purposes. Well, because the potential energy, okay, is radially in all directions, and because all the distances are maximized, it doesn't cancel completely, but essentially, the potential energy here, the potential energy due to the nucleus and the electron interactions are minimized, okay? Also, the potential energy due to electron-electron interactions are also minimized because the distances between the electrons are minimized, right? But you could sort of think of it this way, right? In iodide, because the distances here indicated in blue are a lot larger, the potential energy due to the electron-electron interactions should be far lower than it is in chloride. In fact, it should be lower than it is in bromide and a lot lower than it is in fluoride. Okay? Meaning that overall in iodide, because the electrons are so far apart from one another, that overall the potential energy is the lowest for iodide. That means also, because the potential energy is the lowest, it's also the most stable. Now suppose I apply some kind of electric field to somehow force all these electrons into one octant of the atom. Well, again, in chloride, they're some distance apart still. They're closer than they were in the first case. Certainly the distances are not maximized anymore. They're actually a lot smaller. So the potential energy goes up there. If I do the same thing, apply a similar electric field to the iodide, I'm still going to force these electrons into this octant of the sphere, but the distances are still, the inter-electron distances are still a lot larger than they are in chloride. And so the potential energy in iodide with the electric field applied is still going to be also a lot lower than it is in chloride. Okay, so here the radiuses, the distances are a lot larger. Here they're a lot smaller, so iodide should have the lower potential energy even when the electric field is applied because there's more volume for the electrons to occupy. And that ultimately has to do with the size of the atom, therefore the radius. So here's ultimately the key. We're going to do a little comparison in this. We're going to recall these identities right here. Which has a larger distance between electrons? This is the inter-electron distance, iodide or chloride? Well, it's iodide. It has a larger electron distance, which means which one has the lowest electron-electron potential energy? Which one's going to have the lowest potential energy? It's iodide because the inter-electron distances are a lot larger. Now, remember that potential energy has a lot to do with stability, okay? Iodide clearly has the lowest potential energy, therefore it's the most stable. Okay, iodide's the most stable. Why is that important? Well, when you start doing reactions, you're going to start doing reactions in a couple chapters where you have something referred to as a leaving group. The way to think of a leaving group is sort of like this, okay? If you had a can of soda on the edge of your counter, right? And you took a textbook, right? And threw the textbook onto the counter such that it stayed up there, but it knocked the can off onto the floor, the can would be the leaving group, if that makes sense. So you threw the book onto the counter, the book stayed on there, but it knocked the can off onto the floor, can is the leaving group. Well, it turns out that in the case of leaving groups, the leaving group that's the most stable is the best leaving group, right? What's the most stable leaving group? It's the one that's the most polarizable. So what is polarizability, sort of as a definition? The way I would define it is a polarizable atom is an atom in which there is significant amount of space to spread charge over. Charge as in electrons. The more space there is to spread the electron density over, the more polarizable it is. Okay? We'll talk about, we actually in previous videos talked about another way to spread charge over a molecule, that's resonance, but that's not what this is. Polarizability is just within one atom that doesn't have resonance, within one atom, how much space or volume is there to spread that electron density over. If it's really high, it has great polarizability, it's a pretty stable group, and it's a good leaving group generally. So here's a closing question for you now that we've completed all of this. If I were to go to the periodic table, let me indicate some of it. Boron, carbon, nitrogen, oxygen, fluorine. Let's do chlorine, bromine, iodine. Let's even throw in sulfur, selenium here, right? Which one of these halogens is the worst leaving group? Well, the worst leaving group is the one that's the least stable as an anion or just by itself. The least stable one, according to what we just talked about, is the smallest one. So that means this right here is the worst leaving group, which means which one's the best? Well, it's clearly the largest one. Iodide is the best leaving group because it's the most polarizable. It's the largest, has more space to spread that electron density out, spread charge out. We can even do the same analog with the chalcogens, oxygen, sulfur, and selenium. Which one would be the best leaving group according to this group? Well, the best one would be selenium. Selenium would also be the best leaving group. And again, oxygen would also be the worst. Oxygen is the worst leaving group. Okay? So that's like, when you look at a periodic table, it's still useful and organic. You can use it to predict some trends. Which is the best leaving group? Well, it's usually the atom that's farthest down on the group. Okay? So hopefully that makes a little bit of sense. And also what we're going to find in another video later on when we talk about something called a nucleophile. Polarizability also has a lot to do with the power of a nucleophile. Turns out that larger atoms tend to be better nucleophiles. We'll talk about that more in another video. But hopefully this helped you get an intuition on polarizability. And in the next video, we're going to talk about a completely different topic. See you in the next video.